All right, so now that we've talked about dislocations, let's go a little bit more in depth on that Burgers vector we talked about in the last module. And here I just want to clarify something that doesn't really matter that much, but you might have noticed the apostrophe I put in the previous slide. That's an error. It should just be Burgers without apostrophe. It's not possessive. That's just the scientist's name. So Burgers was the scientist's name. So just a clarifying point there. Okay, so let's look a little bit more at the Burgers vector. So this is something that we can determine through a technique or method of looking at a crystal, both a perfect and a distorted crystal, and looking at what we call the Burgers circuit. And so let's kind of go through that in a little bit more detail. So the first step is to look at a perfect crystal. And so this is our perfect crystal of the same material as the one that's distorted over here. And what we do is we're going to make a circuit around the material in the same vicinity that would cover a distortion in the defected material. So we choose a path around the material. So in this case, to encompass everything, what I'm going to do is I'm going to start here, and then I'm going to transition over 4 atoms. So 1, 2, 3, 4 total atoms, right? So I'm going to draw a vector from the start to over here, and then I'm going to go 5 down in order to carry over everything, and then do the same thing in reverse. So the same direction as up top, and then the same, or just opposite direction, same length, and then the same length but opposite direction as over here. So the idea is, in a perfect crystal, this will get you back to the start. So the start equals the end. And so we've created the circuit. So far, it hasn't told us much. But the idea here is that if we now look at an edge dislocation in that material, we're going to do the same thing. So we're going to start at the same atom right here, and we're going to do the same transformation as we did over here. So we're going to draw the same circuit. So 4 over, 5 down, 4 back over, 5 up. So we're going to do that, right? So 4 over, 5 down, and then back 4 and up 5. And by doing that, what we see is that in this case, in this distorted crystal, that the end point is no longer the start point, right? And that's important because the difference is the distortion in this lattice, and therefore the difference here, the direction and magnitude, is the direction and magnitude of the Burgers vector for this edge dislocation. And so this is the way we would do it for a edge dislocation, and we can do the same thing for a screw dislocation, as I try to show down here. So this is again the repeat of the edge, and then you can see here that we're drawing the circuit on the plane that basically perpendicular to the line. So in both cases, the circuit is going to be on the plane perpendicular to the dislocation line. So again, here the dislocation line kind of goes back into the crystal. Here it's going into the page for that. And so we could do the same thing, and we find the circuit in here as well. So the Burger circuit allows us to find the Burgers vector. And here's just a kind of more detailed approach of how we do just what we talked about. So we adopt a viewing direction looking down the edge dislocation for the edge dislocation. We make the circuit clockwise through a defect-free material and take equal steps, number of atomic steps, on parallel sides. So basically make that circuit. And then we do it in the defective crystal, and the difference between the end and the start is the Burgers vector B. All right, so So far we've looked at this, and we've looked at this in hypothetical sketches, right? However, we can actually visualize dislocations in materials. However, we can't do it with typical microscopy like optical, because, as you may imagine, these Burgers vectors, these dislocations, are very small, right? We're talking a difference between atoms here. And so to view them, we have to use electron microscopy, in particular transmission electron microscopy, TEM. And then we're able to visualize the effects of these dislocations. And so in this material, the darkened regions are those distortions, and they are lines. So these are the distortions, the dislocations within a single crystal material that we have. And so we will later in this chapter actually talk a little bit more about electron microscopy and visual and how it kind of gets these images to some extent.